What if I told you that gravity isn't a force pulling you down at all? What if it's actually time itself pushing you into the future? Today, we're going to unpack one of the wildest, most profound ideas in all of physics, the idea that what you and I feel as gravity is really just a distortion in the flow of time. All right, let's get into it.
I know, it sounds like something straight out of a sci-fi movie, right? But this is a real direct consequence of Einstein's greatest work. This one idea completely changes how we see the universe, and it all starts with throwing out that old, comfortable idea of gravity we all learned in school.
For hundreds of years, everyone thought of gravity as this invisible force, like a rope, pulling things toward each other. Simple. But then, in the early 20th century, Albert Einstein came along and, well, he just completely flipped that idea on its head. He gave us a totally new picture where gravity isn't a force at all, but a fundamental feature of the fabric of the universe itself. And this quote from the physicist John Wheeler, it's just the perfect summary. Space-time tells matter how to move, matter tells space-time how to curve. It's this beautiful two-way relationship. It's like a constant cosmic dance happening all around us, all the time.
Now, you've probably seen the classic analogy. You put a bowling ball on a rubber sheet and it creates a dip. That's great for picturing how space gets warped. But here's the secret, the thing that almost every explanation leaves out. The warping of space is a tiny, tiny part of the story. It's not nearly strong enough to explain the gravity we feel every day. The real star of the show is the warping of time.
Okay, so to really get how time itself can be warped, we first have to accept a fundamental and kinda weird truth from Einstein's other big theory, special relativity. And that truth is, time is not absolute. The speed at which it passes actually depends on how you're moving. Let's walk through a little thought experiment to see how that's even possible. Imagine a really simple clock. It's just a particle of light, a photon, bouncing between two mirrors. Each bounce is one tick. Got it? Okay. Now, what happens if that clock starts moving? Well, for the photon to get from one mirror to the other, it now has to travel a longer diagonal path. But, and this is the absolute unbreakable rule of the universe, the speed of light never changes for any observer. So, what has to give? Time itself. From the outside, that moving clock must tick slower. And this isn't a trick. It's a real phenomenon called time dilation. So how do we connect a moving clock ticking slower to gravity? This is where Einstein had what he called his happiest thought. It's called the equivalence principle, and it's brilliant. It just says that there is absolutely no difference between feeling gravity and feeling acceleration. If you're in a sealed room, you have no way of knowing if you're sitting on Earth or if you're in a rocket ship accelerating through space. That feeling is identical. And this idea is the crucial link.
And this is where it all clicks into place. If acceleration is the same as gravity, and we know that motion, which is related to acceleration, causes time to slow down, then it follows that gravity must also cause time to slow down. But here's the big leap. This isn't just a weird side effect of gravity. This slowing of time is gravity.
The old way of thinking had it completely backwards. It's not that gravity is some force that, by the way, also happens to mess with clocks. No. It's that time flows at different speeds in different places. And it's that difference, that gradient in the flow of time, that we feel and call gravity. Right now, time is flowing just a tiny fraction faster for your head than it is for your feet. And every object in the universe is just trying to follow its natural path through space-time to age as much as it possibly can. And that path, through this warped time, is what's pushing you down into your chair.
Let's try to picture this. Think of time as a direction you're traveling in. Near something massive, like Earth, that road of time gets distorted, kind of compressed. So for you to travel what feels like 1 second on your bumpy, compressed road, someone far away on a nice, smooth time road has actually traveled much further. They experience more time passing for every single tick of your clock. That right there is gravitational time dilation.
Okay, this all sounds incredibly abstract. I get it. But physicists don't just cook these ideas up and call it a day. They test them. And to do that, they use the most extreme environments the universe can provide, turning the entire cosmos into a giant laboratory.
You know, our own solar system is actually pretty tame, gravitationally speaking. It's what physicists call a weak field environment. So to really push general relativity to its breaking point, we need to look at places where gravity is ridiculously strong and things are moving unbelievably fast. We're talking about things like binary pulsars and the areas right around black holes.
And near a black hole, this time warping effect just becomes insane. Seriously, just look at these numbers. If you could spend just 24 hours orbiting a black hole pretty closely, almost 2.5 days would have passed for everyone back on Earth. Get even closer, and your one day could stretch to more than 44 days for the rest of the universe. You would literally be traveling into their future.
And this is where the theory smacks right into reality. What you're seeing here is data from two pulsars spiraling into each other. The blue dots, those are the actual measurements, collected over years. And that red line? That's the prediction from General Relativity. The theory says the system has to be losing energy by creating ripples in space-time, what we call gravitational waves. And just look at it. The fit is perfect. This was the first concrete proof we had that these space-time ripples were real.
General relativity is just an astonishingly good theory. It describes our universe on the biggest scales perfectly. But there's one place it falls apart, the weird, bizarre world of quantum mechanics. And so, the ultimate quest in physics today is to unite these two worlds into one single theory of everything.
One of the most famous contenders for this master theory is string theory, and it asks us to completely reimagine the universe at its most basic level. What if particles aren't points? What if instead everything is made of tiny, one-dimensional vibrating strings?
In this picture, every different particle we see, an electron, a photon, is just a different note being played by one of these fundamental strings. And here's the crucial part. One very specific vibration corresponds to the graviton, the quantum particle of gravity. It all fits together. The only catch? Well, it's a big one. For the math to actually work, string theory needs our universe to have extra spatial dimensions, all curled up so tiny that we can't possibly see them.
So, it's been a heck of a journey, right? We started with gravity as a simple pull. Then we reimagined it as the actual curvature of time. And now we're looking at a reality that might be woven from tiny vibrating strings in dimensions we can't even perceive. It really makes you wonder what other incredible truths about our universe are just sitting there, hiding in plain sight.